So let's now consider the principle of superposition for voltages. For voltages. The basic idea is actually to build upon the principle of superposition for electric fields. And it goes something like this. If we want to know now the voltage to go from point A to point B, or from B to A, we know from the definition of our basic definition, from our very basic definition for voltage, that it's going to equal minus, I'm just copying this formula here up above, minus the integral from A to B of the electric field, whatever it is in this particular situation that we're trying to understand, whatever that total electric field is, and then we're going to integrate that total electric field dot dx. Next, we use our ordinary principle of superposition. We know that this total electric field can be written down as a sum of the electric fields that are contributed by each and every point charge that makes up our system. So this might look something like this then. That's going to be minus the integral from A to B. And now instead of E tot here, we're going to substitute in the electric field from, say, the first point charge in the system, E sub 1 pt, if you want to call it that, plus E sub 2, etc. And all of those, that entire sum then gets integrated dot dx. Now as I think about this, actually what I'm writing down doesn't apply just for superposing a bunch of point charges. It could work for any electric field distribution. So let me actually remove this constraint here that I'm talking about point charges. Let's just think about an total electric field that is from some combination of any type of fields, from point charges or lines and planes or whatever it is we might like to do. The next step in our proof uses the fact that you're all familiar with, that the integral of a sum should equal then the sum of the integrals. So I can then break this integral up into a series of contributions, one coming from each of these various electric fields. So there'll be minus the integral from A to B from the first electric field dot dx. Then I'll get the next contribution, but remember our minus sign, minus the integral from A to B of the electric field from the second contributing distribution dot dx. And these are vectors, of course, minus, and so forth. Now the magic comes in. Here, I'll just slide this up here a little bit. The magic comes in because we can recognize that this integral here is the very definition, right, of the potential, the voltage, associated with whatever this first charge distribution is. It's just the integral of E1 dot dx. So this then would be the voltage associated with distribution 1 to go from A to B. The next term then is just going to be the contribution that comes from the voltage that would be associated from charge distribution 2 as we go to B from A, and so forth. So if you look at what we've managed to accomplish, this sum, if we trace it back to its origins, just like we'd written the total field in terms of the sum of these electric fields here, so this sum here was actually just coming from the total field. In a similar way, this whole thing traces all the way backwards in our derivation, that what we are getting then is the total potential. I'll call it V tot. And so V tot, then, the potential associated with the total field in going to B from A is nothing other than the sum of the potentials for each of the contributing fields in going from A to B. Now, this then gives you a very powerful way, just as we have for the principle of superposition for electric fields, to get electric fields for complex situations. This quickly allows us to get voltages for complex situations. It has another very important theoretical value, which is this now allows us to prove that, in fact, voltages are indeed conservative, that the calculation of voltage is path independent. We've proved it here for the point charge, but the beauty is that any charge distribution ultimately is associated with some set of point charges, all of the electrons and protons, for instance, which make up the system. And since each of the terms individually are path independent, we know then that each of these contributions would be path independent, and so therefore the total sum then would be path independent. So now we know that voltages are path independent, even if it's not just a single point charge. Path independent for any distribution. And that's very critical for us, as we're going to see. It has very important implications, actually, for circuits and makes up one of the key laws for circuit analysis.